While we live in an incredibly connected world, there are still many places on the planet where no communication network exists. In emergency situations, either natural or man-made, our traditional communication systems can fail when we need them the most. I've been working primarily in South Sudan for the last decade, and have often seen a need for a modern communication system that can operate without an existing network. I began actively working on this system because of a specific need. We work with a very remote hospital in an area without any communications network. The hospital also operates a number of very basic clinics in outlying areas. Because of the terrible conditions of the limited road network, it can take several hours to reach some of these clinics by road. There are also very few vehicles in the area. The major issue we're seeing is people would come to the clinics with issues far beyond the capabilities of the facilities. For example, women with obstructed labor who needed C-sections. Because there are no vehicles available, the women would either need to walk or be carried to the hospital. Or someone would need to be sent to the hospital to get them to send a vehicle. The process could take many hours, which could be too long in time-critical cases. I looked for communications options available commercially. There are traditional options using VHF, UHF, but the systems are bulky, expensive, and require trained operators. I wanted to be able to create a simple digital interface that would be intuitive for someone even without a technical background. I also wanted to be able to incorporate different sensors and GPS information, which would be very difficult with an analog system. Satellite-based systems also exist, but the high monthly cost and complexity of managing such a system would mean it would not be sustainable without continued outside intervention. There are a few commercially available systems that try to meet a similar niche. One is Gotenna, and another is called Beartooth. These are designed to pair with a mobile device and give a radio link. While these are neat devices, they were not quite right for my situation, and because they're closed source, there was no easy way to modify them. While looking at these projects and trying to come up with open source alternatives, I came across references to people using LoRa chips to send SMS messages. LoRa is a long-range spread-spectrum modulation scheme developed by Semtech, who manufactures and licenses the technology. These chips are readily available standalone or as part of a number of development boards. There are several open source projects using LoRa as comms devices. It seems most of them got to the point of proof of concept, then didn't take the idea further to an actual rollout. While I looked at these projects, I found they didn't quite work for me, so instead of forking an existing project, I decided to start from scratch. However, I am deeply indebted to the open source community for publishing their work to point me in the right direction. I'm also utilizing a number of Arduino libraries, including Sandeep's Arduino LoRa library and the Little V graphics library, along with others. It is really nice not having to get lost in the weeds and being able to focus on the specifics of this implementation. I appreciate the tremendous effort involved in writing and maintaining these libraries. The specific geography of the area I'm working in has pushed some of the design decisions for this project. Specifically, the area that I work in is filled with jutting hills locally called mountains. Because of this, I knew I would need some sort of repeater system on the top of the mountains to communicate with clinics on the other side. The name of this project is Jebel, which is actually a transliteration of the local word for mountain. There are different ways to create a network of connected devices for a project like this. All of these methods have their advantages and their disadvantages. The simplest method, which is used in traditional walkie-talkies, is a peer-to-peer network. In this typology, all nodes communicate directly with each other without any intermediary. Messages can be addressed to specific nodes or to all nodes. This has the advantage of being simple to set up and only requires 2 nodes. You can also have great flexibility in the locations. It has the disadvantage of being limited to the range of the device. Another typology is a star configuration, where all units send and receive data via a central node. This is the system that is utilized in the LoRaWAN, where all nodes report to a central gateway. In this system, nodes do not communicate to each other directly, but only via the central node. This has the advantage of a centralized network that can be controlled and allows for monitoring. But it also has some specific disadvantages that both devices need to be in range of the central node. You have a bottleneck at the gateway, and you can have a situation where nodes are right next to each other but can't communicate because they can't reach the central node. Another typology is a mesh or repeater mesh, where every node also acts as a repeater. This has the advantage of giving the highest chance of a message going through, as in theory, as long as there is a chain of nodes between 2 nodes, they will be able to communicate. This could be a very effective system in a network with only a few nodes. However, it quickly becomes problematic with something like LoRa, which takes a long time to send messages, because when multiple nodes start repeating a message, it can create interference so that all the messages become corrupted. It has the advantage that it doesn't need an established network and it's highly flexible, and any node can communicate with another node. But it has some distinct disadvantages in that it can't deal with numerous nodes in the same location, and nodes will potentially interfere with other nodes. Jebel utilizes a hybrid system that tries to take advantage of the benefits of the different systems, but limits the disadvantages of each system. This is being called the hybrid repeater network. In this system, each node has a unique address. All nodes have the ability to communicate with any node in range, like in a peer-to-peer network. If a node receives a message, it will send back a message received confirmation to the sending node. In this form, only two nodes are needed for communication, and they can work anywhere that they are in range of each other. If the message is not received by the node, however, after a set amount of time, the node will send a command to repeat the message. Nodes designated as repeaters will repeat the message, and later the message received confirmation. These repeater nodes would be stationary nodes placed on hilltops, which maximizes the line of sight, which is critical for LoRa messages. By only allowing nodes with the best locations to repeat the message, there is much less noise than in a completely meshed network, which maximizes the chance for a message to get through without creating interference. LoRa messages are low bandwidth, which means that large messages could take considerable time to send. With higher spreading factors, long messages could take seconds to transmit, so making a message header that is as small as possible is critical. For Jebel, the message header is 5 bytes. The first byte is the message address, where the message is going. The second byte is the message sender's address, who sent the message. The third byte is the message type. Is this a text message or a received confirmation or some sort of command? The fourth byte is the message ID, which identifies the message, and the fifth byte is a checksum, just to verify the message integrity. Messages with LoRa can be up to 256 bytes, so with this header there are 251 bytes available for message content. Currently the address is 1 byte. This allows for up to 255 devices on the network, with hexadecimal 0 being allocated to send to all devices. If these spaces were not enough for the devices on the network, the addresses could go up to 2 bytes, which would allow for 65,535 devices, but it would add 2 bytes to each message, 1 byte for message address and 1 byte for sender address. It is better to stay at the 1 byte data address unless more devices are needed. All messages have the 5 byte header attached to them, but many messages do not need any additional information besides the header. 256 possible pre-configured messages can be sent by changing the value of the third byte. For example, 1 byte is sent to request the current battery voltage of a node, another to get the current GPS location, and another is used to confirm message receipt. These short messages can communicate a lot of information without needing a great deal of on-air time. Nodes and repeaters can utilize a number of different hardware sets to communicate on the Jebel network. Any Arduino-compatible board can be used as long as they are capable of communicating with a LoRa module. Currently, the major focus is on the ESP32 platform, because it allows for multiple UARTs, which allows for serial communication to computer, next-gen display, and GPS unit concurrently. It also allows for Bluetooth or Wi-Fi connections, though those are not currently implemented. The low-power processor on the ESP32 also allows for low-current deep sleep to allow for long battery run times. My first device utilized a TTGO T-Beam, which includes an ESP32, Neo6M GPS, and SX1268 LoRa module. The GUI runs on a 3.5-inch next-gen display. It is powered by a 2000 mAh LiPo. The case is a generic waterproof case with a 3D printed insert to hold the hardware. I'm currently working on porting Jebel to the TTGO T-Watch, which has a built-in LoRa radio and GPS with an ESP32 and a 240 by 240 capacitive touchscreen. The system is currently working to send messages, but there is still a lot of work left to develop features and to improve the code. I'm hoping to get a basic version running well in the next few months, and then if everything's going well, I plan to install the system at the hospital by the end of the year. I hope that it will be a system that is helpful to others trying to develop a similar project. I'm releasing this project under the GNU GPL version 3 license. Thank you to the open source community for providing inspiration, direction, and a model to work together to solve major problems.